Hello. We want to discuss today the Newton's second law of motion. How do we apply it to rotation problems? Okay. So rotation. By now, you should have learned these things. Angular displacement, which is the angle uh, around the axis that is rotates. It can rotate, if I'm looking from one side of the axis, it can look as a clockwise rotation or counterclockwise rotation. And so not just the angle, but which way it's rotating. So if it's counterclockwise, we assign a positive number for the angle. And if it's clockwise, then we assign it as a negative number. So similarly, angular velocity can be counterclockwise or clockwise in the rate at which the angle is changing. And then acceleration alpha can be the same way. How is this velocity is changing? If it's speeding up clockwise, then this is also must be clockwise. If omega was counterclockwise and slowing down, then this will be clockwise, and so on and so forth. So you should have some practice of this by now. If not, maybe you want to go ahead and do some more homework problems or some example problems in the book and have more clear ideas of what these are, because they are the description of the rotation itself, and we are entering now as to what causes that. That means if you are unclear about this, it's going to just compound your or make it more difficult to do anything in rotation. Okay, let me pause it for now. Okay, let's resume our conversation. I had a call just now. Okay, so I was saying that you really need to know these things before you can actually do the other things. All right, so those are very fundamental and must be understood first. We also learned a thing called angular momentum, this product of moment of inertia with angular momentum. This omega can be clockwise or counterclockwise, so this gets same thing as omega, and I, the moment of inertia, has many different formulas for it, depending on the situation, and they all come from a fundamental reason you want to tell how difficult it is to rotate something. The further away from the axis something is, the more difficult it would be. But it's not just if you double the distance from the axis. If the axis was here and you were here and you double the distance, does not mean your resistance or inertia doubles, actually quadruples 4 times. So it's a very strong effect, the distance. And so formulas look like mr squared, and I was using capital R, mr squared if you have a single particle from, it was going a circle of radius r. If you had 2 particles and each one was going into its own radius, so it will be like that. If you have a bar, then if you were a bar of mass and length L, and you are trying to rotate about an axis to the edge, then it was ml squared, but you had to divide by 3. It wasn't just like those formulas, it was actually this. And if I had a disk and you are spinning the disk, so the disk is a solid object like that, and this would be half mass times the radius of disk is r, and mass is m. So, etc. You may ask me, do I have to memorize all of that? No, actually you don't memorize that, but this is something you should memorize. For a single particle, it's like this. Because in some sense, all of these are variants of that, you know. Okay, in an exam situation, you would be given maybe this formula will be given. This is something all people tend to memorize also, but this all the other formulas will be given to you if needed. Okay. We also learned a concept called torque. So if I have a force F acts in some point, we want to know how much influence this force will have in rotating, and that's called torque. And that torque is we had a procedure: follow the lever arm procedure. Okay, so once we have these things under our belt, we can say what is the second law? Second law of Newton is about motion, right? So about acceleration. So second law of Newton, second law you had said is a force. You probably you remember a force. This is a vector quantity, and this is abstract. So force is equal to force causes change in momentum. So there are two ways to write this. The rate at which momentum changes is this, and if this also, if mass is not changing, like you don't have a rocket problem or some other things, you can write it as m times acceleration. Okay, so you have a second law, and if it's in calculus, you will be write instantaneous. It will be dp dt, and this would be the case if mass is not changing, if mass fixed. And we are going to mostly deal with the mass fixed problems. Okay. So this is what we have done a lot. Now I want to say, I want to kind of change this to a rotation. So I want to know the torque applied by this force. If I replace this force by the torque applied by this force, what would have happened to these guys, right? So if you have a calculus background, you can derive on those things, but I'm not going to derive this here. So I'm saying that if this force, that's over here, so I have a lever arm, so I multiply this with the lever arm of the force, right? And then so I'll get a torque of this force. So if I do a torque, what will happen to the right side? And you will be not surprised that this actually is the momentum becomes angular momentum. So this is the more fundamental one. Or if you were even going more fundamental than this, you would have a vector torque, and you would have dl dt. You go, but we are not going to go there. But just wanted to show you that calculus is needed if we want to go further than this. Okay, so I have a angular momentum. This is all about an axis. About an axis. So the torque about some axis. The angular momentum is about the same axis. So there. And what happens to this guy? Well, if I look at inside here, it's a delta of I times omega over delta t, right? Now you can see right away that if this moment of inertia was not changing, if the moment of inertia was not changing, so I can say if moment of inertia I not changing. What does it mean? Moment's not changing. So let's see how, if you look at just one particle, okay? If this is going in a circle, how would the moment of inertia can change here? Mass can change, right? So if mass does, so mass has to be fixed, or it can change in a different circle. So if a particle, if this is the axis and the particle is going in this circle, and for some reason it's actually started to go underneath like this, it's still going around this different circle, then moment of inertia will change. If I have two bodies, so suppose I have a dumbbell and I'm kind of rotating, this guy's going in this circle and this guy's going in that circle. Well, if the dumbbell is a rigid thing, they will continue to go in the same circles. This is the axis you're rotating, right? But suppose the dumbbell was not rigid, like us. Our arms are not rigid. So I may be spinning, but I pull the arms in. So somehow what happened was, at some point, this was not your regular dumbbell, but some other dumbbell where it was with time, at some time it's that distance, and sometimes it's with that distance. So this is T1, this T2, and it's rotating about that. So when that is happening, you will see the moment of inertia change in time. You have a larger moment of inertia when it's T1, and it's going to be a smaller moment as a T2. So we're saying that we are not looking at so-called non-rigid bodies. We are not rigid bodies, right? We're looking at blocks, buildings, bridges, beams. So those are rigid bodies. And once I have established an axis, I'm not moving around the axis. Okay? So that means this means fixed axis. So number one, I have a fixed axis. Number two, what do I have is the body is rigid body. So it's not like that. It's more rigid like that. Rigid body. When I have this kind of condition, which will be most cases for us, okay? We'll do a couple of cases where I may be changing. But when that's the case, then I can come outside here. And so you have I times delta omega over delta t. So you don't have to just make a product and then look at the change. You can just say I outside and then just look at change in delta omega t. So that's equal to I times alpha. So the torque, after all of this, this is the more fundamental law. All of this is equal to I alpha. So often we write it like this. We say that moment of inertia times alpha for rigid bodies, for rigid body fixed axis. So for rigid bodies fixed axis, we're not moving the axis around like we're spinning a disc, by rotating the bike wheel. So for those situations, what we have is torque equals I times alpha. So this is going to be a replacement of F equals ma when we are dealing with rotation problems. Okay, so you can see a couple of things, that this is also I didn't write vector here, but it's also a vector equation. So for instance, this when you look at the direction, if this is counterclockwise, so if this has a counterclockwise sense, then this will be counterclockwise sense also. If this has a clockwise sense, then alpha will also be clockwise sense. And the way, if you want to put a plus minus thing, if this turns out to be plus, then this will also turn to a plus. If this is minus, this is minus. Equation wise makes sense, like, but this is the direction. So this equation, when we apply, we're gonna do another video application of this equation. We're gonna say what's the magnitude and what's the direction, right? So that we need to be able to extract two information. So magnitude just look like this equation, and we extract information about the sense of rotation. Or sense of direction. If you wanted to use actual axis, and if you were to rotate everything in the XY plane, so your bodies were rotating in XY plane, so the axis will be that, axis will be Z axis. So sense of rotation will be replaced with a right hand rule. You remember the right hand rule, right? If you know, there's a video on the right hand rule too. You can go check out this video. So it either gonna, right hand rule thumb will go up towards the plus Z axis or minus Z axis. So this happens when you have a counterclockwise, and this happens when you have a clockwise. So sometimes sense of rotation, you can give a direction and write all of this as a tau of Z, the Z component, equals I alpha of Z. Sometimes you write it like this. Or you can just follow this more physical picture of saying which is sense of rotation. And either way, they're equivalent. They're capturing the same information. So there's not like one is superior to the other. This is more algebraic, and this is more conceptual. All right, so I'm going to stop this video. This is a pretty good introduction to how Newton's second law of motion is used into solving rotation problems. And once I get alpha, with alpha I can actually tell what the omegas would be. If this is constant, then there's a constant acceleration formulas that help us do that. I can say how much rotation took place. So once I get an alpha, I can feed into that and kind of learn more about the rotation that would result as a result of some forces and some torques associated with those forces. Okay, so next video I'm going to try to set up a problem where I can find some application of this equation. Okay, see ya, bye.